Well, good morning, afternoon, evening, wherever you are, and welcome. Now, I'm sorry that Global Atheist News overran a couple of minutes. If you've been coming from that previous show, thank you for watching that too. But yes, sometimes there's a lot of news. I find it difficult to cram it down into a half an hour or less. Anyway, today, FreeThought Hour is a bit different from usual. So I have to confess that I don't have a guest, not a live one anyway. Now, this is because I did line one up, but unfortunately, he wasn't able to turn up on the event. So next week, we've got a guest. In fact, I can give you a heads up for next week, because we will be having the president of Atheist Alliance International, Howard Berman. I'm very pleased that he's agreed to be my guest next week. So today, what I'm going to do is show you a little clip from an event that happened earlier this morning, earlier today. It's evening here now, and it features yours truly and Lawrence Krauss. So I'll just share that screen, and you'll see that it's Lawrence being a guest speaker at the AGM of AUK. Here we go. Well, welcome everybody. Thank you very much for coming. And a special welcome to our guest of honor, Lawrence Krauss. Hello, Lawrence.
Hi, it's nice to see you.
Yeah, well, we missed seeing you last year, didn't we? When we'd set up this meeting in the Conway Hall, Red Lion Square, and COVID came along and stomped on it. So
yeah, I felt really bad. That's one of the reasons why I wanted to come to make a quick hello and see everyone today at the meeting. I felt very badly that last year I was looking really forward to being at Conway Hall again and with you all, and then COVID came along, and we're all getting used to doing things online. My Origins Project Foundation had several events scheduled, and of course they've all had to be canceled. We've rescheduled them for 2022. Our first event is with Noam Chomsky and Jeffrey Sachs in January of 2022, if all things go well, and we'll see what happens in the US. It's in Phoenix, and it'll be held online. But and even this AGM now is online. Yeah. So
yes, indeed.
So we all have to learn to live with that. And but you know, there are good things that come, as we have to remember that as well. And at least for me, having for the first time in my life having all of my events, public events everywhere canceled and travel canceled. Yeah. It was the first time I didn't travel, and I suddenly discovered that I could do things I didn't do before. I wrote my new book, which came out in March. Normally books take me at least a year to write. I wrote that in 10 weeks because I just was able to work 12 hours a day at home. And I thought, well, I'm not a first line responder, but maybe I can do something useful for the world. So the physics of climate change was when it came about, and it's now become more relevant than ever. The new IPCC is just coming out, and I think it's important for all of us, including your group, to think about those issues that are really relevant, so people don't waste their time on silly superstitions and begin to think about how the world really works, so we can know how to address it in the 21st century. And so I really wanted to just provide my encouragement to all of you to keep up the good work and out there, and I hope that I can join you in real time at some time in the future.
Wouldn't that be nice? Yes. So the physics of climate change is in hardback at the moment. Is it coming out in paperback soon?
It's coming out in paperback. I think it'll come out in the new year in paperback. It's in England. It's published by Head of Zeus. And in fact, I met that publisher through my friend Richard Dawkins, who made an introduction for me, and I'm very happy to be working with them. They're now actually a part of a larger publishing company, Bloomsbury, but they were independent when I signed on with them, and I'm actually, my next book I've agreed to do with them as well. Oh, right. And yeah, in fact, I think I have You can tell me which cover you like better, because I have.
No,
this is the American cover. Okay, and then the British cover is this. So.
Ooh.
Yeah, so the British cover, they decided that this would work better for. It's funny how publishers decide the sensibilities of different people are sensitive to different colors. But in any case, that's that book.
So yeah, well, anyway, Lawrence, sorry to interrupt. I think publicity for your book may end up on our website.
Oh, well, that would be nice. You know, that'd be nice, because one of the things that's interesting, and this is relevant to all of you, is that I had a heck of a time finding publishers for this book, because for a variety of reasons. But one of the things that was mentioned by a lot of publishers is that they didn't want a book about science, which is what this is. This isn't policy. This is the science behind climate change that dealt with things. They wanted something that was sensational. They wanted something that was doom and gloom and appealed to emotion. And at least 4 different publishers said, yeah, if you just wrote something that was emotional and explained that the world was going to end, we publish it. And I think it's really hard and really important for people to cut through that emotional nonsense and sensationalism, and to try and deal with the real world, which is one of the things I know that your organization's about.
It's a sad truth, isn't it, that narrative counts more than reality, than information.
Well, there's lots of things that count more than reality right now in our public times. Pseudoscience, in our country, wokeism, and you know, and just claims that if it doesn't agree with your a priori belief, and this is kind of the other thing, is that, as I've said once in fact recently at a debate at Oxford University, that we're seeing, and I don't know if your group will deal with it, but we're seeing lots of kinds of religiosity, if you want to call it that, or theology, not just the standard religions, but people are feeling that if it disagrees with what they believe to be right, it must be wrong. And of course, the world is the way it is, whether you like it or not. And that's unfortunately in our country, in both in the U.S. and now that I moved to Canada, it's the same. People policies are being based on what people would like to believe is true instead of what really is.
I call it religionism, because that makes it sound more like racism, which is it's very similar to.
Yeah. Well, in some cases, it is that. Insisting that people identify by race seems to me to be something that I thought we'd gotten over a long time ago.
No, sadly not. Yeah. So, are you going to start cruising again soon?
Well, that kind of cruising, yes, I'm going to be. I'm going to be. The Origins Project is actually, well, in fact, there's still a few spots left, and we're having a trip from Iceland to Greenland, and in September of 2022, and it's a chance for people to spend a lot of time intensively with people they might want to spend with. So there's 3 guest speakers. It's September 8th to 21st. The cruise, starting in Reykjavik and moving up to the coast of Greenland and back down, and then we'll have an additional add-on in Iceland. But there'll be 3 guest speakers: myself, an individual who won the Nobel Prize in physics a few years ago, Barry Barish, for discovering gravitational waves, and another special guest, Richard Dawkins. So people who want to spend 14 days with all of us, and a bunch of wonderful, and we found that the guests on this trip, our trips, are as interesting as the speakers, and some of them are coming from England already, and so we have about five berths left in our allotment on that ship. It's a ship that's 128 people. We'll probably have about 40 people, which is about the right number. I don't want it to be too big. It's not cheap, but for 14 days.
Anybody want to sponsor me to go? Anybody sponsor me? President's perks, maybe.
President perks. Well, if you come, we'll donate a little bit to the organization, but just a little bit. Because unfortunately, Arctic expeditions are not cheap, and I wish we could make it cheaper than we will. And the add-on, the Iceland add-on, both Richard and Barry and I will be on the add-on. It's going to be an event at the University of Reykjavik. We haven't finished those things, but that add-on will be separate, and people can sign up for that. That'll be actually a lot less expensive. Anyway, It's just a hop, step, and a jump from England to Iceland.
Yes.
As the Vikings discovered.
Yes, indeed. Yes. Hmm.
In any case, I hope if some of you want to do it, it'd be great to have you and the Origins Project. Of course, I'm hoping over the long term and with you all. We're hoping to do events around the world and co-sponsor with different groups. And I'm hoping that maybe we can do something together at some point.
Well, certainly, if we can think when traveling is possible again, for you to come and perform for us, present to us, then we love that.
Yeah, no, well, I would too, and maybe we can talk about climate change, which is not all doom and gloom. It's there's a lot of interesting science, and so for me it was it'd be kind of I think it'd be kind of appropriate to do such a thing for the group in Conway Hall. So fingers crossed, even though that's rather superstitious.
That's very
maybe in the new year we can all do something together in the UK. That'd be great.
That would be great. Yes, indeed. Should we let it go now, guys?
Yeah, I've got to take my dog out for his morning walk, but I thought it's nice to see all of you, and thank you all for doing what you do. I just wanted to say that as well.
Thank you for being our guest.
Okay,
Thank you, Lawrence.
Okay, you take care.
Thanks, Lawrence.
Okay.
Bye-bye.
Bye-bye.
Yeah, well, he's right, isn't he? Because climate change is very interesting to scientists, and if anything can save us from our own fate, our own self-harmed fate, then it'll be the scientists. It won't be those who pray. So, what made me think, having met him again this morning and enjoyed a conversation like that, it reminded me that a while ago, it must have been probably 2019, I interviewed him on my then show for 45 minutes. So I'm prepared now to show you that interview. Now, he's not here, obviously. I am. So if you do want to ask any questions that I might be able to answer, feel free. And I will interrupt the video and deal with anything going along if that's what you require. So I hope to hear from you. Right, now I'm going to show this other video. You'll see it's a much younger version of me. Where are we now? Not that. No, go away. How did that happen? This one. Share screen again. Window. This one. And go. Right, now we're going to make it big, can't we? Can we make it bigger than that, but not huge? I'm not sure about that because we lose the audio if we do that. So I'm just going to click go. Hello, welcome, and how the devil are you? Tonight, we've got somebody who needs no introduction, so I'm not going to give him any. Here he is.
Hi.
Hello, Lawrence.
How are you doing?
We've got an echo on your end. I don't know what's going on.
You should because just check this on my end. I think that's fine.
It's my point. It's got an echo, so it doesn't matter.
Okay.
I'm not going to speak much. You're the guest.
Okay. Good. Okay.
Okay. So
we'll see how that goes.
yeah. So welcome to everybody who from anywhere. And Lawrence, you're going to introduce yourself to the people, will you? And you're a world famous cosmologist. Could we start by explaining the difference between some of these words? You know, like cosmologist, physicist, astronomer, astrologer.
Yeah, I think the biggest confusion is between cosmologist and cosmetologist. But anyway, I've been called a cosmetologist in the past. But I think if you look at me, you realize that. So I'm a theoretical physicist, trained originally in particle physics, but the study of the large-scale picture, origin, and evolution of the universe is a field called cosmology. And because it allows us to test our fundamental ideas, our fundamental understanding of physics at its most basic scales, that's why I've gotten interested in cosmology. Cosmology, of course, in some sense encompasses astrophysics, which is the physics of astronomical objects. We often use that astrophysics to try and probe different parts of cosmology, to understand galaxies and stars if we're exploring the age of the universe, for example, or the nature of black holes and that sort of thing. So there's clearly cosmology encompasses astrophysics is many different areas, some of which have no cosmological particular relevance. And of course, astrology is just garbage.
Well, I can't argue with that. So
I should say it's based on ideas that are almost 3,000 or a little over 3,000 years old.
Yes.
Which had no basis in anything we had about the universe now, and the fact that people still talk about it 3,000 years after it should have is kind of amazing.
Yes.
Anyway.
Well, it depends on pattern recognition, doesn't it? Our brains seeing shapes and imagining what they might be in the night sky.
Well, yes, but it's like any con job. If you convince people that you're talking about them by being actually big and sufficiently complimentary, people will assume it has substance.
Yes, yes. There was an interesting test, wasn't there, where they got 12 different people in a different horoscope, and they gave them all the same reading, and they all said it suited them, a perfect match.
They've done that, but my one was sent. I took the horoscope of a well-known serial killer, and sent them to people, and everyone found it was their horoscope too. So anyway,
well, enough of that. Let's get down to some serious physics. What's the next question on my list? Oh yes. Fans of sci-fi movies often get to hear about something called pure energy. Now, as a retired science teacher, that grates with me because the only energy I know is something that does work, and we can only detect it when it's doing work, when it's changing from one form to another. But you're the physicist, you tell me.
Well, I think that what to kind to some of the people who use those terms, of course, energy comes in many, many forms. It's manifested is sometimes just in the rest mass of an object in general, in special relativity, sometimes in the work you do, chemical energy, the energy I store from eating donuts or whatever, and potential energy, the energy I get by climbing up a mountain. That if I do work to do that, I gain energy when I'm up at the top, and I can do work if I jump down and land on someone. But energy, I think the point is that there's a kind of energy which is the energy of light, of radiation, and electromagnetic radiation. And since light has no mass, I think some people, and it's not necessarily good terminology, but light has energy, but it doesn't have mass. And so when something is in a form of radiation, I think some people would call that pure energy. It's not all energy is pure in one way or another, but what I think they mean is that it's energy that's not associated with rest mass. So I'm willing to be generous and I say that they're not completely misapplying that term, although it doesn't have any significance on its own. Light has energy. It also has momentum, by the way, even though it doesn't have rest mass. Light bounces off you. You may not feel the recoil, but it's significant enough that we're some people are using the idea of light as large sails that into space that have the light from the sun or a laser beam hit on them and input momentum on them. In fact, I was involved for some time in a project along with late Stephen Hawking used to be involved in this that by a Russian billionaire who's been proposed creating little small satellites with sails and on the ground that power those little teeny spacecraft and get to 20% of the speed of light. It doesn't violate any laws of physics. It probably violates a lot of engineering principles. The more I learned about it, the more I got involved in it, the more skeptical I became that we'd be able to do it. But it uses the momentum of light. And so light has energy and momentum, just no mass. I'll answer to a short question.
Yes, I remember something in school when I was teaching years ago, and a glass bowl evacuated with a rotating, silver on one side, black on the other.
Yeah, it rotates because the black side absorbs light energy. And I mean, there's a number. It's not quite in that case. The answer isn't just the momentum of the light. In this case, what happens is that the black energy and heats up, and the air behind it adds additional pressure that pushes it forward.
So it was expansion. It wasn't an evacuated.
Well, I haven't worked out the details, but it's evacuated, but it's never completely evacuated, and the heat energy is enough to basically the exchange of heat between it and the rarefied gas is also relevant, and I suspect that's more relevant than the momentum transfer. In fact, I'd be amazed if it wasn't the case.
Yes. So until they work out the actual mass of light, we're going to think of that as close to pure energy for the.
Well, I mean, did you say a massive light? Light is definitely massless. There's zero doubt about it. And only massless objects can travel at the speed of light. That's a central principle of special relativity and general relativity. And so, I mean, we measure, you have to test these things. And photons, the particles that carry light, the particles that convey electromagnetic radiation are called photons. And they are massless to the highest activity we can measure, less than about 1/millionth of a billionth of maybe a millionth of a millionth of a billionth of the mass of an electron. Doesn't prove they're massless, but now I should say that's only in empty space. The interesting thing that happens is that when you put light in a medium, and in some mediums, it can act like it has a mass. In fact, in metals, light acts like it has a mass, but in empty space, it doesn't. So what appears to be mass depends upon the medium and that may sound exotic and relevant just for light. It's true we think at a more fundamental level, because we think the mass of all the elementary particles we measure, protons, quarks, electrons, we think is due to the interaction with a background field, which we call the Higgs field. That's why, and so the greatest story ever told. I described how those are similar. The fact that light gets mass when it goes in a metal is very similar to what we think is the process that happens for all particles traveling through this background Higgs field. And if this Higgs field didn't exist in empty space, particles would essentially be massless, and the world would be quite different because you and I wouldn't be here to talk about it.
Mm-hmm. Well, I think you've gone well over my head already.
Okay. Well, I've been waving my hands over my own, so it's okay.
So I've got another one here. The solar system has shape, hasn't it? It's flat in the middle, and it's a disk, isn't it?
Oh, you mean the galaxy? Well, the solar system is a disk too, almost. Not all. There's something called the ecliptic, which is the plain solar system, but some of the planets are off the ecliptic. But our galaxy is a disk, and we've actually taken pictures of it. It's a large disk about a size. The radius of the disk, or the diameter of the disk, is something like 100,000 light years across, and maybe it's about somewhere like a few 10 light years, maybe between 1 and 10 light years thick.
Mm-hmm. So what about the entire universe? Does it have a shape?
No. Not in the sense that we can. First of all, we see no boundaries of our universe, and we talk about the universe now in a more precise way. We talk about the observable universe, which is really all we can talk about. And our observable universe has no edges, no boundary, no anything. Now, it's possible that space closed in on itself, that you might see that we haven't detected that. There was another aspect which is a little more subtle, which is something called topology, which basically could say that the universe has a weird, not geometric, but a topological structure, sort of like topology. He said coffee cup has a hole here, and therefore I could make a donut. One hole has the same topological properties regardless of its geometric shape. And it's possible that our universe can have weird topology, and some people have proposed that, but there's no evidence of that either. So our universe has no, except locally, the geometry of our universe, because universe can exist in three types of geometry: open, closed, and flat. A flat like a pancake. It's just the universe where the X, Y, and I'll say Z, or X, Y, and Z axes are perpendicular, and they say in everywhere. In a universe with curvature that's either open or closed, if my axis, at some point it's going to curve in a different direction. So parallel lines will diverge or converge. Again, our observers is as accurately as we can flat. So straight lines are straight as far as I see them.
We've got a poor connection, I'm afraid. We're catching some of your words, but not all of them.
I'm sorry. I think maybe some due to my my Wi-Fi. I'll repeat that again if it's okay. Then I'll just say that the geometry of our universe can be in one of three different forms: so-called open, closed, or flat. And difference is just what light does, or what your coordinate axes do: X, Y, and Z. In a flat universe, they always point in the same direction everywhere in space. Whereas in an open or closed universe, if you move through space, they curve away. So in an open or closed universe, light rays either diverge or converge. Parallel lines either diverge or converge. But as far as we can tell in our universe, to the best accuracy we have, light rays go in straight lines.
This reminds me of non-Euclidean geometry.
It's exactly what it is. Non-Euclidean geometry is the geometry that describes universes that can be curved. Euclidean geometry describes a universe that's flat. Mm-hmm. And what is amazing is we appear to live in a universe in which Euclidean geometry on the whole works very well.
Yes, useful.
Yeah, it makes it easier.
Yes, absolutely. So you're famous for having for lots of things, but in particular for having written a book called A Universe from Nothing.
Mm-hmm.
So what is nothing?
Well, I wrote a whole book about it. So, and I have to say, I got philosophers and theologians angry at me because I said that not only would that some of them would get angry at me anyway, and because they're experts at nothing, but and they didn't take that well. But the point is that nothing is a very subtle concept, and it's a concept whose meaning has changed over time. Obviously, it's the absence of something. Is one simple way of you're describing it by the converse. But as our notions of what something is have changed, and they certainly have, so has our notions of nothing. In the Bible, for example, the nothing of the Bible isn't nothing. It's a vast, eternal, empty void. It's like we thought space was, with nothing in it, but it still had space, right? Now we know that empty space is not so empty. It's a bubbling, boiling brew of virtual particles. But that biblical definition, no one seems to mind when people complain that scientists have changed the definition of nothing to suit them. They don't realize that we have too. That if they don't like the nothing of empty space not being nothing, then they shouldn't like the nothing of the Bible, because that's exactly what it is, a big empty space. So, but you can say, okay, well, empty space is not nothing because there's space there. And you might say, okay, well, get rid of the space. There's no space, there's no time, there's no particles. That's a much better definition of nothing. And I point out that exactly that kind of nothing can produce a universe full of particles and galaxies and people without any supernatural shenanigans. But then when I do that, people who still don't like the idea say, well, that's still not sufficient for me, even though it would have been sufficient for me if you hadn't said what you said. But so just having no space, no time, no particles, no radiation, that's not good enough. I'm sorry, my screen keeps blacking out. And what we can do is I can try and call you back from my laptop instead of my computer, and that should work better, maybe. Would that be better?
Give it a go.
Okay, I'll try that. Okay.
You're back.
Okay, is this better?
Good. We can hear you.
Yeah, are you getting
That's
an
much
echo?
better.
Okay, are you getting an echo or not?
No.
Okay, then
No, it's
I'm gonna put on my headphones.
it's
Okay.
all good. So that question we had come in is on the subject that we were already dealing with.
Okay, I see it. It's pretty bleak. I don't see why. First of all, first of all, we don't know what the future brings, right? That's it's like the Charles Dickens story. It's the future as it might be. In the future, it's what is reasonably certain in the future is that everything we now see will be gone. Namely, even matter is likely to decay. So the stuff that makes us up and all the galaxies and stars that we see is likely to go away. And so the space will become cold, dark, and empty. But that's
This is tomorrow, though, is it?
It's not tomorrow. No, in fact, we're talking about a time frame which is far longer than the life age of our sun. I've already said this before, but our sun's gonna encompass the Earth in about 5 billion years. It'll stop burning hydrogen. It'll swell up like a red giant, what's become known as a red giant, and its radius will encompass the current orbit of the Earth. So we'll be toast, literally. But that's a long time. That's 5 billion years in the future, and I've made this joke many times because it's about some person like me talking about this, and someone in the audience puts up their hands and says, "Did you say 5 million years?" And the speaker says, "No, 5 billion years." The guy goes, "True." The point is that we're now talking about a time far longer than that. When matter will decay, we know matter has a lifetime of at least 10 to the 32 years. That's a million billion years, and that's that. So there's nothing. It's not worth worrying about. Now, it turns out in a much shorter time frame, if we're right, we're observing the expansion of the universe to be speeding up, and that means distant galaxies are receding from us faster than light, which is allowed in general relativity. They're actually at rest in their own frame. The space between us and them is expanding so that they're receding from us, so that the light from them never reaches us. Light travels through space, but it can't catch up. It's like a swimmer trying to overcome an undertow in the water. But it turns out if that continues, if that expansion continues, then every galaxy we can see outside of our own galaxy, every out of our own cluster of galaxies, actually, all the distant galaxies that we now can see in the universe will disappear at a time scale of about 2 trillion years, which again is 2,000 billion years. So not worth worrying about.
I won't start getting insurance then.
You can get insurance. It doesn't hurt. But it won't pay off your lifetime.
They'll want to sell it to me, that's for sure.
Yeah, that's right.
Yes.
In fact, I'll be happy to sell you that kind of insurance. You want to buy it from me? No problem.
Yes. So there's another question. That's from Steve.
What's my preferred interpretation of quantum mechanics? I'm glad you asked this, Steve, because it's such a red herring. People waste so much paper, and especially in times of climate change, I hate that, just talking about the interpretation of quantum mechanics as if it's some big deal, as if it's something profound. My preferred interpretation of quantum mechanics is quantum mechanics. Namely, when we try to interpret quantum mechanics in terms of a classical picture, we come up with crazy things. But that's not so surprising, because the world at its fundamental scale is quantum mechanical. we, on our scale, we see things classically because quantum mechanical correlations wash out. So we experience a world such that the world of quantum mechanics seems crazy, and we have to try and frame it in terms of arguments that make sense in our classical world. But that's ridiculous. I mean, there's no reason for quantum mechanics to make sense in a classical world. So, as my late friend Sidney Coleman, who was at Harvard when I was there, and a brilliant, wonderful lecture called "Quantum Mechanics in Your Face," which you can watch online. It's technical, but it's wonderful nevertheless. But he said what's really important is the interpretation of classical mechanics, not the interpretation of quantum mechanics, because what's fundamental is quantum mechanics. So you want to interpret the classical world in terms of the quantum mechanical world, not the other way around. Having said that, I mean the classical interpretation I think comes closest to trying to capture much of the craziness of quantum mechanics is the many worlds interpretation. Nothing new about it. I know books have been written recently about it, and it's like 50 years old, and nothing's changed. And it's the idea because it fundamentally in quantum mechanics, quantum objects are doing many things at the same time. And when we measure them, we pick out of the many things they're doing one. So if a spin is spinning, it's spinning in all directions at the same time. We measure it, boom. Say it's fine, it's spinning and it's pointing up this way. Well, in that case, it's like we pick one example out of an infinite number of examples, and the many worlds interpretation says each time you make an observation, basically the universe is splitting into branching into an infinite number of branches, and you pick one, and then every other time you make an observation, you pick another. So the world is multiplying at every instant because these quantum universes, you could have picked another. You could have been in another universe where instead of measuring it this way, you measure it that way. Well, that captures some aspect of it, but does it have any profound meaning? Absolutely not, that I can see. And I think it's a waste of time I don't think it's worthy. I mean, it's worth thinking about these things, of course, but is it worth tomes? I'm not sure. I don't think so.
We had a recent BBC series, I think it was co-produced with an American company called Devs, which I don't know if it's come over to your neck of the woods.
I know it very well. I know the person who created Alex Garland. He's a friend, and I just recorded a podcast with him. So if you watch the Origins podcast with Lawrence Krauss in the coming months, you'll see it. So I've talked to him a lot about quantum mechanics. I know the context of that theory, and we actually discussed it before it was produced.
It was great bit of drama, kept you wondering. There's a lot of silence in it, but it wasn't an action movie, but it was the mood that was gripping.
I haven't gotten to see it yet. I was at the studio when they were making it, and I haven't gotten to see it yet. So
it's worth a binge watch.
Okay. My wife doesn't like science fiction, so I'll have to watch it when she's not around.
I see. So we've got another question here, which is about black holes. That was bound to come up, wasn't it?
Yeah, look, I have lots of ideas with black holes. I haven't published it. If I haven't published them, it's because I don't think they're worthy of publishing. I will be doing a lecture tour. I mean, I've been lecturing and writing about black holes, and I may do a new book on them, in fact. But I think the thing about black holes that confuses me the most still, the fact that I talked a little bit about in my recent 5-minute physics series that I did during the pandemic, and that is the fact that what you see from the black holes have a finite lifetime. They'll evaporate even in the frame of an observer far away. But if you watch them form, they take an infinite amount of time to form because observers seem to freeze, or if things falling into a black hole freeze on the horizon. So you have this object that appears to take an infinite amount of time to form, but decays in a finite time. And that's part of the problem of black hole evaporation. I've actually written a paper with colleagues that suggests that maybe the event horizon never forms. Maybe black holes evaporate before they form, which would solve a lot of problems. It has its own set of problems, I should point out, and I think by no means is it universally accepted. But I guess my views regarding black holes is that you should treat much of what you hear and read about black holes with a grain of salt, in the sense that there are still puzzles, many puzzles of black holes that haven't been solved. And ideas of a firewall at the event horizon are fascinating, but I think it's right now, there are so many contradictory bits of way of thinking of black holes that to try and resolve these problems, people come up with plausible possibilities that are motivated in some sense by underlying theories, and mostly in the most recent cases, they've involved string theory. And because string theory, there's no evidence that string theory actually describes reality, that while these ideas are interesting, then it's not clear that they describe the real world. So I guess what I'd say, my strongest theory about black holes is watch this space, because I think we have a lot left to learn about them. And I don't think the paradoxes of Hawking radiation, information loss, and what happens at the event horizon are yet resolved in a way that many people outside of the authors of those papers would accept. I mean, the community has views, and I think that they're fads, but it's a fascinating, that what makes black holes fascinating is they up front and in your face present the contradictions between general relativity and quantum mechanics, which is really at the center of trying to understand fundamentally how our universe came into being. So black holes are fascinating as test objects. Every time you can find paradoxes in physics, it means that it encourages you to look for new ways to think of things. And that's what people are doing. And they have lots of new ways to think of things, but it's not clear which is right.
But the general public don't like that, do they? They for a start, they don't realize that there's sort of two realms. There's sort of what goes on in here, which I like to call the conceptual realm, and then there's what is actually out there, which we might call the natural realm. And so we can think of all sorts of models that might be explanations, but until we've matched them with observations, we don't know which one is correct, if any.
Yeah, that's right, and we don't mind being wrong. That's the point. No. We don't mind presenting things and being contradicted by the evidence, because that's how it works. It doesn't work. Politicians don't like that, and many other people, but that's the way science works. Most things are wrong, as I keep pointing out. Most of the proposals I've made about the universe are wrong, not because I made mathematical errors, but because the universe wasn't smart enough to obey them.
To agree with you.
And so, right at the forefront of physics, there's all sorts of models that people present, and each of them in some ways is a straw man to try and see if we can propose an experiment that could rule it out. And that's what's great, because as I say, you can't prove things to be true, but you can prove things to be false. And if you get rid of all the false stuff, as Sherlock Holmes would say, then what's left over is probably right.
So this is a big problem for believers, isn't it? Because they really desperately want certainty, and we can't give it to them.
Well, believers, I mean, that's the point of, if you know the answer to the questions before you ask the questions, which is what religion is all about, it's highly suspect. And that is the problem. The idea of absolute truth, which doesn't even exist in science, is an anathema in some sense. And the notion that you can't, that our understanding won't change and evolve is also, it's more important, it's countered by everything we know about human history and science. Science is that we know a lot more now than we did a century ago, and that's because we're willing to change our minds. And whereas the sacred books are the same as they were 2,000 years ago or 1,400 years ago, or you pick your sacred book. And the fact that they haven't changed is good evidence that they really never were right to begin with.
So did you become an atheist, or were you born one?
Well, look, I hate to label myself, as you know, but I don't label myself by things I don't believe. But what happened is I grew into, in the modern parlance of an atheist. I was, brought up and I read the Bible and I read other things. I grew up in a Jewish house, and I wanted to believe, like most people do, just like I wanted to believe in Santa Claus or the Easter. Well, these are anyway. And all that happened was that as I learned more about the world, those stories became clear to me as fairy tales, and eventually I had to recognize that as much as I wanted to believe, the statements made there were completely contradictory with everything I knew about the world, and they didn't have any insight. And so it wasn't an epiphany. it was just a slow realization that, as much as I wanted to believe these stories, they obviously were nonsense. And I wish, I could say that it was obvious to me when I was 5 years old they were nonsense. Yeah. Maybe intrinsically it was, but I was probably in my early teens before I was willing to, unabashedly say that.
Yes. I don't call myself an atheist either, because like you, I think it's ridiculous to have a category that depends on a lack.
I relabeled myself various times in honor of my late friend Christopher Hitt. For a while, I called myself an anti-theist because if you look at the God of the scriptures, the thing you'd want is that to be. But the term that I use anything now is an apatheist because I don't give a damn. God is so irrelevant to everything that I do as a scientist and a human being that I don't even think about it. And that's the really important issue, because somehow people seem to think, and it's groups like the Templeton Foundation and others that have somehow given people this false impression that scientists worry a lot about God. They don't worry about God at all. I've been a scientist for 40 years. I never heard the term mentioned in any scientific meeting. It's an unimportant issue because you don't have to think about God to understand the universe.
Mm. Interestingly, well, at least interesting to me, if it hadn't been for lockdown, I would have debated Hamza Tzortzis, whom I saw on YouTube. You debated a little while ago.
Yeah, well, you were saved that. That's good. You should feel glad about that.
Well, I did one in February with what's his name, Imran. No, can't remember. But another.
Anyway, the useful thing, if there was a useful thing in that debate, and I gather there are, because people have written and said they've gotten something out of it. It wasn't a pleasant experience for me, but was that they segregated it, and it was at the University College London, and
yes.
And I objected, as you know, and the useful thing that came out of that is the public outcry as a result caused them to be rejected from being allowed to hold any public events at universities because they weren't respecting the secular nature of the society in which they lived. And so I suppose that was a useful byproduct.
So this is something that we've been debating in our group for some time. Is maths real? Is it invented or is it discovered?
Math. You mean math?
Yeah, math. Sorry.
Mathematics, as I would say.
Yes.
Well, look, I mean, that's the kind of, I try to avoid those kind of philosophical questions. I think the point is, mathematics is a tool that describes the universe, and it appears to be it appears from everything we can say, the language in which nature operates, the appropriate language to describe nature. Now, obviously, it's a human invention, but in the sense that humans have, developed that, just like the standard model of particle physics is a human invention. But
it's not
what we discovered at the same time, because what we discover is that those rules work. And we discover, more importantly for mathematics, that generally they work to describe the universe. Although the important thing about mathematics is it describes a multitude of universes, only one of which is ours. And mathematicians, therefore, don't have to worry about reality. We physicists do. And I think Hermann Weyl, I wrote in one of my books at the end that he used to say, when, as a mathematician, he often had to choose between truth and beauty. And in all cases, he chose beauty. Mathematicians have that luxury, but physicists don't. At least physicists other than string theorists.
Yes, well, a lot of people don't realize that maths is modeling, or science is modeling. And
it's a summation to reality. There's no scientific theory that's absolutely true on all scales. In fact, we have a rigorous way of proving that. And so they're all models of reality that are ever better models. But the language to describe those models is not English or Czechoslovakian or any human language except for math. Math is the only way to capture properly models, is the only way to model the universe in a way that works and allows you to make predictions.
Yes. And if the equations don't work, then we make better equations.
Yeah, well, if the equations don't work, or we throw them out. If your predictions don't work, you throw them out, or you refine them depending upon the model and what the predictions are and everything else. And so, But mathematics is a language of modeling. And for some reason that that is amazing, it happens to be the right language to describe nature. And it's because mathematics has many more things than just it has more things than just a grammar. It has interconnections that other languages don't. So Feynman wrote about this. So you can say sentences. I can say the following sentence: the force of gravity varies inversely proportionally to the square of the radius between objects and proportional to the product of their masses. That's Newton's law. Or I can say planets go around the sun in orbits that are ellipses, where they cover equal areas and equal times. In English, those are two separate sentences. In mathematics, they're equivalent.
Right.
That's the important thing about mathematics. I see another question here.
It's similar to gravity being the same as acceleration.
Yeah, my feeling about this is that it's probably wrong. You should be wary when you see a paper saying this. It's what are your thoughts about the idea that the fine structure constant appears to vary across the universe and have certain direction to it? Well, the point is that newspapers and magazines love to write about strange results. What they never write about is when the strange results aren't confirmed. So I'm an agnostic. I'm a skeptic and agnostic about everything, especially new scientific papers. And I'm betting dollars to donuts that you find that fine structure constant doesn't vary across the universe. I know this idea has been proposed for a long time, and in particular one group has constantly tried to measure this. And what the results are interesting, but they've never been compelling to me. And so I think the jury is still out here, and I'm betting against it. But I'm happy to be wrong.
I wonder what Sean Carroll would have to say about that.
I'll bite my tongue.
Okay. Nothing mentioned. Best not said.
Yes. Mm-hmm. Yeah.
Let me have a look for another question. Yeah.
And I'm sorry, I will have to go in a few minutes because I've got another event here in about 9 minutes, just so you're aware.
Yeah, sure. Okay. We were scheduled to finish in 9 or 10 minutes.
Yeah.
So,
okay.
So you deserve to escape, but maybe
mm-hmm.
maybe you'll come back another day and we could.
Sure. Especially since we screwed up in the technology for a few minutes, so we lost some time.
Yeah. Thank you. So what have we got here? We've done the fine structure constant. What else have I got in my list? Why is there plenty of matter and no antimatter?
Well, I don't know whether we can talk about that just in this little bit of time. It's the question. It's one of the questions at the heart of applying particle physics to cosmology. It's the thing that got me and many other people into cosmology, because a sensible universe should have equal amounts of matter and antimatter. In the sense that matter and antimatter weigh the same amount. In the early universe, if you had a lot of energy in the form of radiation and it could create matter, as can happen in particle physics, it should create equal amounts of matter and antimatter. And in order to have a universe with more matter than antimatter, you need very specific rules that Andrei Sakharov, who was the dissident Soviet physicist and father of the Soviet H-bomb, came up with these 3 rules that that the laws of physics need to have in order to create dynamically a universe which has more matter than antimatter. Because what happens is if you don't need a lot more matter than antimatter initially. Right now we don't see any antimatter. But the point is there could be a lot of matter and antimatter in the early universe, but if there was a slight asymmetry, all the matter annihilates except there are just a few parts over in any given volume, and that's enough to account for everything we see. So we now see about 1 to 10 billion particles of light, photons, for every proton in the universe. And if matter and antimatter are annihilated early on, and every particle of matter annihilated with particle of antimatter producing photons, then all you need is an asymmetry of 1 part in a billion early on, so that you eventually leave only matter left in the universe. And that's the idea behind most of the physical theories we have for why we live in a universe made of matter alone, which is that there was very slight asymmetry, and then if you have that slight asymmetry, it could be explained it can explain everything we see. The big problem is what created the slight asymmetry. And the answer is, we don't know. We know what the requirements of the theories are. And when Sakharov proposed those theories in 1967, the physical models that we had of the universe didn't have any of those features. Now the models we create have all of those features, and we don't know if any of them are right. But we certainly can create models that do what's required, but we don't know if nature obeys those models. And unfortunately, it's difficult to experimentally test, although there are detectors called proton decay detectors, which if a proton ever decayed, that would be evidence that matter could disappear. And we think it does, but we now know that the lifetime of a proton is bigger than 10 to the 32 years. So you have to build bigger detectors. How can you do that, right? If a proton lives much longer than the age of the universe, how can you measure its lifetime? The answer is you get a lot of protons, because quantum mechanics is probabilistic. If the average proton decays in 10 to the 32 years or more, all you need is 10 to the 32 protons, and on average, one of them will decay every year. And that's why we have these huge underground water detectors trying to look for protons to decay, and we haven't seen any yet. If we do, it'll give us some better idea of how the universe came dominated by matter.
Wow. So I'm not going to ask you whether the Big Bang is really the start of the universe, because that would take too long in the remaining time.
Yeah, well, the answer is we don't know.
Yeah, okay.
Something like the Big Bang is the start of our observable universe. If it's the start of everything, is a very different question, and mostly metaphysics. But I think many people would say now that it's not likely the start of everything. It's just the creation of our universe, which is pretty relevant for us, since most of us live in our universe, except for the president of my country and maybe the prime minister of yours. But anyway, maybe that's a good way to end. Is that a good way? Is that okay to end it that way? And I'll come back again after I've spoken enough people.
Before we get on much of a ice there, I think. Okay.
Okay.
Laura, thank you very much.
Sure. Thanks. Thanks for the questions, and I will come back. Thanks. I appreciate it. You take care.
Take the rest of the day off for now.
Okay. Take care. Bye-bye.
Bye-bye. Well, I don't know about you, but I enjoyed rewatching that. I really enjoyed rewatching that. I'm sorry about the quality. Honestly, this was back in the beginning of lockdown when nobody knew how to Zoom or use any of the current technology. I've now sorted out the necessary amount of light, and the green screen is working fine, except when I do that and the shadow goes across it and it all goes fuzzy. But and the sound, I'm sorry about the sound too, because there was a glitch somewhere between wherever he was in, I think it was in Ohio at the time, and where I am too. So I'm sorry about the quality. If you can bear to watch it, you enjoy it. At least I do. So next week, things are back to normal. We have a live guest who you will be able to address questions to, and it's Atheist Alliance International's president, Howard Berman. So think about that. Like, share, comment, set the notifications, all that nonsense, and I'll see you again next week. Let's see if I can find the outro. Yeah, here we go. Bye-bye. Thank you for watching.